In today's video, I'm going to explain about vector spaces. This is just the brief introduction of vector spaces. Suppose we have a non-empty set V and a field F, and we have two binary operations, addition and multiplication. So the first one, vector addition. Note that the elements from V are called vectors and those from F are called scalars. And you should not confuse vectors used in this one with the physical quantity, those vector quantities such as velocity, force, and so on. Here, vectors are just the elements from this vector space V and scalars from a field F. So in the vector addition, we take two vectors from V, then if we add them, it should belong to V. This is the vector addition. The second one, we have the scalar multiplication. We take any scalar from F and a vector from V. Then, if we multiply A with U, this one should belong to V. So, under what conditions this vector, this V will be called a vector space over a field F? So, V over F will be called a vector space if the following conditions or axioms hold. So the first one would be for addition. So we denote by A1. A means addition, okay? The first one, commutativity of addition. If we take two vectors from V, then U plus V should equal to V plus U. This is the first axiom, okay? And then the second one, A2, associativity. Now we take three vectors U, V, W from V, then U plus V plus W should equal to U plus V plus W. This is the associativity of addition. Next, A3. There is a vector in V denoted by 0, okay, such that for any x, let's take U, such that for any U in V, this condition is satisfied. U plus 0 is equal to 0 plus U is equal to U. This is the third one. And then A4. In A4, for any U belonging to V, there is a vector denoted by minus U which belongs to V such that U plus minus U is equal to minus U plus U is equal to 0. And next, okay, this A1, A2, A3 and A4 is for addition. So we are left with the multiplication. So let's denote that one by M, okay? Let's say M1. Now, first take two vectors from V, okay, and take a scalar, say K, from F. Then add these two vectors and multiply with a scalar. This one should equal to ku plus kv. M2. Now next, what you do? Take two scalars. Suppose a and b from F and take one vector from V. Then add these two scalars, multiply with a vector. This one should equal to AU plus BU. M3. Now in M3, take two scalars from F. F is a field, okay? And then multiply and take one vector from V. Then multiply these two scalars with a vector. It should equal to A bracket B U. This is M3. And the last one, M4. Take one, which is a scalar from F, and which is a unit scalar. And take a vector U from V. Then 1 into U should equal to U. This M is for the multiplication, okay, and these are for the addition. So if all these axioms hold, then we say that V is a vector space over a field F, okay? V is a vector space over a field